Today, we're exploring Retrieval Augmented Generation, or RAG, a transformative approach that addresses fundamental limitations of large language models. Hi, I am Vivian Aranha, and I will be walking you through this short video on RAG based on my personal experience. RAG connects AI to external knowledge sources, allowing models to reference authoritative information before generating responses. This technology prevents hallucinations, overcomes knowledge cutoffs, and ensures accuracy without expensive model retraining. By retrieving relevant information and augmenting prompts with this context, RAG creates AI systems that stay current, provide trustworthy responses with source attribution, and adapt to specialized knowledge domains. As organizations increasingly deploy AI solutions, RAG offers a practical, cost effective path to more reliable and useful AI applications. At its core, RAG is a process that optimizes the output of large language models. Rather than relying solely on what the model learned during its training, RAG introduces a critical intermediary step. Before generating a response, the system first searches through and retrieves information from an authoritative knowledge base that you specify. This fundamentally changes how the AI creates responses. Large language models like GPT-4, Claude, or Llama are incredibly powerful tools. They've been trained on vast amounts of public data up to their cutoff date. However, RAG takes these capabilities further by enhancing responses with authoritative, up to date information from sources you trust. This means the model can reference your company documentation, specialized databases, or recent information that wasn't part of its original training. What makes RAG particularly valuable is that it creates a bridge between general purpose language models and domain specific knowledge. For example, a healthcare organization can connect an LLM to their medical databases, ensuring responses reflect their specific protocols, research, and patient information. Similarly, a manufacturing company can ensure the model references their unique processes, equipment specifications, and safety procedures. A significant advantage of RAG is that all this improvement happens without having to retrain the underlying language model. Retraining these massive models requires specialized expertise, enormous computational resources, and can cost millions of dollars. RAG bypasses this need entirely. The model's fundamental capabilities remain unchanged, but its responses become informed by your specific knowledge base. This makes RAG an exceptionally cost effective approach to tailoring AI capabilities. Organizations of any size can implement RAG systems to improve accuracy, maintain compliance with industry standards, and ensure AI outputs remain relevant to their specific context. Rather than building a specialized AI from scratch, RAG lets you leverage existing models while directing them to your unique information resources. In summary, retrieval augmented generation represents a practical and efficient way to enhance AI capabilities with specialized knowledge, making language models more accurate, relevant, and useful for your specific needs. Now let's explore the concrete benefits that retrieval augmented generation brings to organizations implementing generative AI. RAG offers four major advantages that address both technical and business challenges: cost effectiveness, currency of information, enhanced user trust, and greater developer control. First, let's talk about cost effectiveness, which is often the most immediate concern for organizations exploring AI implementation. Chatbot development typically begins with a foundation model. These are the large language models accessible through APIs that have been trained on broad, generalized data. The traditional approach to customization would be retraining these models with your specific data. However, this process is prohibitively expensive, often costing millions of dollars, requiring specialized expertise and demanding massive computational resources. Many organizations simply can't justify this investment. RAG offers a dramatically more cost effective alternative. Instead of retraining the model, you simply connect it to your existing knowledge bases. This approach democratizes generative AI technology, making it accessible to organizations of all sizes, not just those with enterprise level AI budgets. Additionally, implementation is faster. Rather than waiting months for model retraining, RAG systems can often be deployed in weeks or even days, providing immediate value while controlling costs. The second major benefit addresses one of the most frustrating limitations of standard LLMs: their inability to access current information. Every foundation model has a knowledge cutoff date, creating an information gap between training and deployment. RAG elegantly solves this problem by allowing developers to provide the latest information to generative models. You can connect the LLM directly to frequently updated resources, whether that's your internal documentation, industry research databases, or even live data feeds from news sites or social media. For example, a financial services chatbot using RAG could present the latest market data. A healthcare assistant could reference the most recent treatment protocols, or a customer service AI could stay current with product specifications even as they evolve. This capability is particularly valuable in rapidly changing fields where information quickly becomes outdated. Instead of providing responses based on 2022 data in a 2025 conversation, RAG ensures users receive the most current information available. Eh, The third benefit of RAG is perhaps the most important for long term adoption: enhanced user trust. AI systems are only valuable if users actually trust and use them. RAG significantly improves trustworthiness by allowing the LLM to present accurate information with clear source attribution. Responses can include citations or references to original documents, creating transparency about where information originated. Users can verify information independently by checking these sources, which is particularly important in contexts requiring high accuracy like legal, medical, or financial applications. This verifiability dramatically reduces the black box perception that often surrounds AI systems. By reducing hallucinations and inaccurate responses, RAG creates a foundation for genuine user confidence. Over time, this trust translates to higher adoption rates and more effective AI integration into organizational workflows. Now that we understand why RAG is important and its benefits, let's explore how it actually works. Retrieval augmented generation transforms the way language models process requests by adding a critical information retrieval step before generation. This seemingly simple change creates a powerful enhancement to standard language model capabilities. Let's start by comparing the standard LLM process with the RAG approach. In a traditional LLM setup, the system takes a user input, processes it through what it learned during training, and generates a response. It's entirely dependent on information it encountered during its training phase. RAG fundamentally changes this workflow by introducing an information retrieval component. When a user submits a query, the system first searches external knowledge sources for relevant information. It then combines the user's query with this retrieved information to create an augmented prompt. Only then does the language model generate its response. This approach combines the best of both worlds: the powerful reasoning and language generation capabilities of large language models with the precision and reliability of retrieving specific information from trusted sources. The result is a system that can provide more informed accurate, and contextually relevant responses. The first step in implementing a RAG is establishing your external data sources. External data refers to any information outside the LLM's original training that you want the model to reference. This can come from multiple sources such as APIs, databases, or document repositories. The data may exist in various formats: files, database records, long form text, and more. However, language models can't directly work with these raw formats. This is where embedding language models come into play. Embedding models convert your text data into numerical representations, essentially translating words and concepts into mathematical vectors. These vectors capture semantic meaning, allowing the system to understand relationships between different pieces of information. These vector representations are then stored in specialized vector databases optimized for similarity searches. Think of this process as creating a knowledge library that's accessible and understandable to your generative AI system. Each document or piece of information becomes a searchable entity that can be retrieved based on its relevance to incoming queries. When a user submits a query, the RAG system needs to find the most relevant information from its knowledge base. This happens through a process called relevancy search or similarity search. First, the system converts the user query into a vector representation using the same embedding model used for the knowledge base. Then, it performs mathematical calculations to identify which documents in the vector database are most similar to the query vector. Let's consider a concrete example. Imagine a smart chatbot that answers human resource questions for an organization. If an employee asks, "How much annual leave do I have?" the system will convert this question into a vector and search for similar vectors in its database. The search will retrieve highly relevant documents. In this case, perhaps the company's annual leave policy and the specific employee's leave records. The relevance is determined through vector similarity calculations, such as cosine similarity, which measure how closely the query vector aligns with document vectors in multidimensional space. This mathematical approach to relevance ensures that the system retrieves truly pertinent information rather than just documents containing keyword matches. Once relevant information is retrieved, the RAG system augments the original user prompt by adding the retrieved data as context. This step uses prompt engineering techniques to effectively communicate with the language model. For example, the system might create an augmented prompt like this: based on the following information, retrieved leave policy and employee records, answer the user question: "How much annual leave do I have?" This augmented prompt gives the language model both the question and the specific information needed to answer it accurately. The model can then apply its reasoning capabilities to synthesize a response based on the provided context. The prompt engineering aspect is crucial here. How you structure the augmented prompt significantly impacts the quality of responses. Effective prompts clearly separate retrieved information from the user query and provide guidance on how the model should use the information. A common question about RAG systems is, what happens when external data becomes outdated? Maintaining current information is crucial for the system's ongoing relevance and accuracy. The solution lies in implementing update mechanisms for your external data. This can be done through automated real-time processes that update vector embeddings as underlying documents change, or through periodic batch processing that refreshes the entire knowledge base at scheduled intervals. For example, when your organization updates its leave policy, the document in your knowledge repository should be updated and its vector representation recalculated and stored. Similarly, as employee records change, those embeddings should be refreshed. This is essentially a data management challenge. and established data science approaches to change management can be applied. Depending on your organization's needs and resources, you might implement different strategies, from simple periodic refreshes to sophisticated event driven updates that respond to changes in source systems. By maintaining fresh external data, you ensure that your RAG system continues to provide accurate and current information to users over time. To summarize how RAG works, the process begins by creating vector representations of external knowledge and storing them in a database. When a user submits a query, the system converts it to a vector and retrieves relevant information through similarity searches. It then augments the original prompt with this retrieved information, enabling the language model to generate an informed response. Finally, to maintain system relevance, external data is regularly updated through automated processes. This complete workflow transforms a standard language model into a system that can reliably reference specific knowledge while maintaining the flexibility and capabilities of generative AI. Now let's explore the important relationship between retrieval augmented generation and semantic search. While these terms are sometimes used interchangeably, they actually represent different but complementary technologies. Understanding their relationship can help organizations implement more effective knowledge driven AI systems. First, let's clarify the relationship between these two concepts. Retrieval augmented generation is the overall process we've been discussing, combining information retrieval with language generation to create more accurate AI responses. Semantic search, on the other hand, is a specific technology that can enhance the retrieval component of a RAG system. Think of RAG as the entire workflow from user query to final response, while semantic search represents an advanced approach to the critical middle step of finding relevant information. Both technologies address the fundamental challenge of connecting language models to relevant knowledge at scale, but they operate at different levels in the solution architecture. When combined effectively, semantic search significantly enhances RAG results, allowing organizations to leverage vast external knowledge sources in their LLM applications. This combination creates AI systems that are both more knowledgeable and more precise in their responses. To understand why semantic search is so valuable for RAG systems, we need to appreciate the scale of the knowledge management challenge in modern enterprises. Organizations typically store enormous amounts of information across disparate systems, technical manuals, FAQs, research reports, customer service guides, human resource documents, and much more. This information often exists in different formats, uses varying terminology, and resides in separate repositories or databases. As this knowledge base grows, traditional retrieval methods struggle to find the most relevant information for specific queries. The sheer volume and complexity create a significant challenge for effective context retrieval. This challenge directly impacts the quality of generative AI outputs. Remember that in RAG, the language model can only reference what the retrieval system provides. If retrieval fails to surface the most relevant information, even the most sophisticated language model will produce suboptimal responses. This is where semantic search becomes critical. Semantic search technologies dramatically improve the retrieval process by understanding the meaning and intent behind queries rather than just matching keywords. They can scan large databases of disparate information and retrieve data with much higher accuracy. For example, when presented with a question like, how much was spent on machinery repairs last year? A semantic search system doesn't just look for documents containing words like machinery and repairs. Instead, it understands the query's intent and can map it to relevant financial documents, maintenance records, or expenditure reports, even if they use different terminology. Importantly, semantic search retrieves specific text passages rather than just document links. It returns the precise information needed to answer the query, allowing developers to provide focused, relevant context to the language model. This granular retrieval capability is essential for creating concise, accurate responses. The limitations of conventional or keyword based search in RAG systems become particularly evident in knowledge intensive tasks. Simple keyword matching often retrieves irrelevant information or misses relevant content that uses different terminology, leading to poor AI responses. Additionally, conventional approaches require developers to manage numerous technical complexities. They must handle word embeddings creation, implement document chunking strategies to break content into appropriate sizes, and manually tune relevance parameters. These technical requirements create significant barriers to effective implementation. In contrast, advanced semantic search technologies automate much of this work. They handle knowledge base preparation automatically, generating appropriate embeddings and document segments without requiring manual intervention. They also produce semantically relevant passages ordered by relevance, maximizing the quality of the information provided to the language model. This automation not only improves retrieval quality, but also significantly reduces implementation complexity, allowing organizations to focus on their use cases rather than the underlying retrieval mechanics. To summarize the relationship between RAG and semantic search, while RAG represents the overall process of combining retrieval with generation, semantic search is a sophisticated approach to the retrieval component that significantly enhances results. By understanding meaning rather than just matching keywords, semantic search technologies help RAG systems overcome the challenges of enterprise scale knowledge retrieval. This results in AI systems that can provide more accurate, relevant, and useful responses across a wide range of knowledge intensive applications.